The day has finally come when we're going to do the bed of death. I'm using the royal we. I will lie on the bed of death, and then we'll put the chest plate of death on my chest. Then the cinder block of death goes on the chest plate of death. And then the assistant of death, Philip, is going to swing the sledgehammer of death, crushing the cinder block of death, death all around. If I make it, we'll talk about impulse and momentum. If I don't make it, semester's over. Okay, everyone gets an A.
Dr. Francis.
But that, Philip, you're gonna pass him some money to. Okay. So let's, given what's gonna happen today, I think maybe we should start with a prayer. Then we're willing to offer a prayer of safety.
Our dear kind Heavenly Father, we are grateful for the chance that we have to be here today and to learn physics. We ask Thee to open our minds and to help us learn by the Spirit. Please help Dr. Francis to teach by the Spirit. I ask Thee to help me not kill Dr. Francis and help us to have a great rest of our day and to really let what we're learning and in all of our classes sink in and change us. And we say these things in the name of Jesus Christ. Amen.
Thank you. That's a good prayer. Let's not kill him. Okay. Let's start with
What is it?
taking attendance.
Oh, now it's.
Okay, now you can click.
They all. Oh.
Just like respond to.
Okay, last call. Okay. Before we actually do the bed of death, let's look at this homework problem, the bobsled jump problem. As you know, back in 2002, BYU saved the Winter Olympics. Okay, they were having all sorts of trouble, and they just asked BYU students to volunteer and to help out up there, and the BYU students saved the day. And my oldest son was one of those students. He was a student at the time that volunteered, and because he was working the event, my youngest son wanted to come down and see what was going on. And the only thing that they could get tickets for was the bobsled. And my youngest son had so much fun watching the bobsled event that he came back excited. And I wrote this test question in response. And what we've got here is a bobsled jump, a new event in the 2002 Winter Olympics. The bobsleds and occupants are launched at point A by a large spring onto a huge semicircular track of frictionless ice. The bobsled teams try to achieve the furthest landing distance level on that landing field. Okay, so the first question was only worth 2 points on the exam. Find the work. You see that it's misspelled. The werk, if any, those are the most important words, done by the ramp on the bobsled as it goes from point A to point B. And the answer, of course, is there's no werk. And that's because if I look at that bobsled, there are two forces on it. There's the gravitational force by the earth on the bobsled, But that's an internal force. We never worry about the Verk done by the gravitational force. Okay, that the Earth is part of our system. The Earth on the bobsled, they're both part of our system. The other force, the ramp on the bobsled, that's an external force. But it's always perpendicular to the track, and the motion is always parallel to the track. And so the question is, does that normal force do Verk?
Yeah.
No, absolutely not. Okay, it's always perpendicular to the motion. Even when we're down there on the track, the force, by the normal force, is always perpendicular to track, and the motion is always parallel to the track. So it does no Verk. Now we get to the guts of this problem, and that is the mass of the Jamaican team. Have you all watched Cool Runnings? Yeah, if you haven't seen that Disney movie, you got to watch that this weekend. Jamaica has a bobsled team. Okay, you'll like it. The mass of the Jamaican team, including the bobsled, is 800 kilograms. If they're traveling at a speed of 50 meters per second, 100 miles an hour, when they reach point B, find the speed constant for the spring. And we're told that the spring constant, the spring was compressed by 4 meters. That's quite the compression there. Okay. Now this is an energy problem, so I'm going to start with the buckets. Initially, the kinetic energy bucket is empty, but there is energy in the gravitational bucket. And what we want to do always is choose the lowest point in the problem as our zero of height. And so even though this is listed as 100 meters, the height up there relative to our zero would be 120. Does everyone see that? Okay, 120. And then we have a lot of energy in that spring bucket. And that gives us a certain amount of total mechanical energy. Now, because that track is frictionless, in part A, we found that there's no Verk done. So that means that the total energy is still the same. We didn't get robbed. So what buckets do we have that energy in now? Well, it's going really fast, so there's kinetic energy. It's still up off my floor by 20 meters, so I've got a little bit of gravitational energy, but the spring is no longer compressed, so I don't have anything in there. Now, if I say my mechanical energy initial is equal to my mechanical energy final, and I write which kinds of energy I have in my buckets here and here, and then I plug in the formulas for those buckets. Now, again, I remind you, these formula are not going to be on your exam on the front page. You have to have those memorized because I want you to recognize those things when you see them in the problem. Okay, and now I'm gonna post the sample exams this afternoon after class, but I don't want you to go rushing to those. We still have some things to talk about, but if some of you want to, get a jump on things and just look for problems that you can handle, but I don't want to scare anyone with problems that we haven't covered yet. Okay. The equations that are on those sample exams will be the same equations that will be on your exam. Okay, you notice I've written K in red, and that's because everything else we have numbers for. Okay, we've got the delta S, we've got the mass, we've got the gravitational field strength, we got the H, everything we know except for K. And that's messy. And that's a characteristic of energy problems. Very quickly, they become algebra problems. Very quickly. And so, as I said before, we tend to get a double hump distribution on this next exam. Those that feel comfortable with algebra and those that really don't. And you know which of those camps you're in, and you might need to work on trading camps before that exam. Now, if I solve that, I get a K value of 25,000 newtons for each meter. See if your neighbor feels comfortable with what just happened there.
Got it?
Yeah.
Yeah.
What?
Yes, sir.
Was the 50 meters per second?
The what?
The 50 meters per second.
Yes, it was given at that point B. Yeah. Okay. Now, part C of this problem asks us to find the acceleration of the bobsled at point B. Now, because a frictionless track does no bear, we can put little bowls or hills or loop-de-loops in our frictionless track. And that gives us an opportunity to go back and revisit centripetal motion. And that's what we're doing here. They're going in a circle. They were speeding up, but they're not speeding up now. They're going to be slowing down, but they're not slowing down now. Right at point B, they're in transition. And so that means that their acceleration vector is going to be perpendicular to their velocity, which is going to point straight up. And it's going to have magnitude v squared over r, centripetal acceleration. And so if I plug in the v of 50 meters per second, which was given in the problem, remember to square it. Sometimes people forget that. We divide by the radius of the circle and we get 25 meters per second squared up. Now, that means that the normal force has to be bigger than the weight force. Why? Because when I draw my free body diagram, it has to scream that centripetal acceleration up towards the center of the circle. That diagram has to have more force up than down. Well, how much more? How loud should that scream? Well, that's always answered by Newton's second law. It has to take 800 kilograms and accelerate it by 25 meters per second squared up. So the scream has to be 20,000 newtons. Is the normal force 20,000 newtons? No or heck no? Heck no. I just got to have 20,000 more newtons than I've got down. Well, the weight force is just m times g, which is going to be 8,000. So if the weight is 8,000, the normal up has to be 20,000 bigger than that, or 28,000. Do another check on your neighbor. Do a buddy check.
Good. Surprising.
I'll take it, you know.
Yeah. It's,
All right.
no.
Really?
You decide.
Okay. Are there questions so far? Okay, how fast will the Jamaican team be traveling right before they land on the landing field? And will this hurt? I think we're sure it's gonna hurt. This is again, an energy problem. If we ignore air resistance, and we always do, energy is going to be conserved. At point B, we've got kinetic energy and gravitational energy, or this total energy that we started with. That's conserved. But if we look right before they land, don't let them land, because then the landing field is going to do a whole bunch of negative arc on them that we can't calculate. Okay, but right before they land, all of that energy is in the kinetic energy bucket because their height is 0. By definition, that's what we chose as our 0 of height. Okay, now if I write those equations down, I've got kinetic, I've got gravitational. At the end, I've only got kinetic. Again, I put in the values or the equations, and I wrote the V in red because that's what we're looking for. Now, in this case, each and every one of our terms has the mass in it, so I can cancel that out. Last time I couldn't cancel it out because we had a term that didn't depend on mass. The spring energy doesn't depend on mass. And so we couldn't cancel out the mass. We had to put it in everywhere it appeared. But this time we can get rid of it, and then we plug in what we know, and we solve for the speed, which is 54 meters per second. Okay? How we doing? Comfortable with that? Okay. Really quick, turn to your neighbor and answer this question. What is momentum? What is momentum?
Dog running. I feel like people.
Can I use you for one of my demos here? Yeah. That's right. I should know that.
Like editing.
Yeah.
Sorry, it does.
Well, no, because higher momentum power.
Okay, so when I say that that senator has a lot of momentum, or that freight train has a lot of momentum, or that idea has a lot of momentum, what does this word momentum tell me about the senator or the freight train or the idea? Hand in the air, raise your hand, brave soul. Yes.
Gonna keep going.
What's that?
Gonna keep going. Keep going.
Keep going. It wants to keep going. Okay. It's hard to stop. Okay. It just wants to keep going. And that freight train had a lot of momentum and was hard to stop. Now, Luke is going to help us here. Luke, do you skateboard? He said he does. He really enjoys it. He loves it. How fast do you skateboard when you're going? About 60 miles an hour, he claimed. That sounds a little high to me, but you know, he wouldn't lie. He wouldn't lie. And so momentum is how hard it is to stop something. And there is Luke going down Cougar Avenue, okay, 60 miles an hour, okay? Now, imagine there's a big old truck right next to Luke, also going 60 miles an hour. Which one has more momentum? Is it Luke or the truck? Shout it out. Yeah, the truck, the truck. Is that truck always going to have more momentum than Luke? No, park it at Albertson. It's not hard to stop a parked truck, okay? So this momentum, the mass matters, but also the speed matters. And it turns out that the formula for this momentum is the product, the mass times the speed. And we use the symbol P for momentum. The M is silent, okay? Or the P is silent. It's like pneumonia. I didn't get that right. I wish we hadn't used P for this, because we use P for power, for pressure, for all sorts of different things. But I wasn't around when they made the decision. Okay. Now, give me an example of something that is hard to stop, but has small mass. Anybody? Raise your hand.
Bullet.
A bullet. Okay. I taught for 31 years in Montana, and I never got a different example than a bullet. And half the time it was during hunting season, and most of the students were in the mountain. Okay. A bullet. And that bullet is hard to stop, not because of its mass, but because of its high speed. I'll give you another example. I went to high school on the island of Guam, and Guam had tropical storms. And what we didn't have were glass windows. Okay, we had these little metal louvers that the geckos could come in, and it was pretty open. And that's because we also had coconuts littering our lawns. Okay, and when one of these tropical storms came around, those turned into cannonballs. And so you didn't want glass windows. Now, I had friends that grew up on the island and had been through several storms. And one of those friends had pictures of a telephone pole that had pieces of glass and pieces of metal embedded in the telephone pole. And that's because the winds picked up these things and got them going so fast that it was hard to stop them. Okay, so you wanted to stay inside when these things were going on. Can you give me an example of something hard to stop that's not going very fast?
Older.
Raise your hand so I can see where the answer's coming from.
Oh, yeah. Steamroller.
A what?
A steamroller. What do you think? A steamroller.
A steamroller. Excellent example. A steamroller. Any other examples we got going?
A boat.
A boat, a big boat. Okay. What about a space shuttle there? Even if it's just lumbering down the runway, it would be hard to stop, not because it's going fast, but because of its huge mass. And of course, this is not the way a space shuttle is supposed to be used. It's supposed to be going really, really fast, in which case it would have both mass and speed and have a great big momentum. Now, is anyone a captain of a boat? Brindley, you have a boat. You're a captain, right? Captain Brindley. Okay, is that your boat? Yes, it is. Okay. Captain Brindley's job as captain is to park that boat at the dock. Okay. And that means he's got to stop it. And that means he's got to change the momentum of that boat to stop it. Now, Captain Brindley, there are different ways to stop that. One way that Captain Brindley could stop that would be to turn off the engine, and I don't know if they've got a key in those things or what they do to turn off the engine, but just to let the water in front of that boat push against the boat and slow it down. Now, Captain Brindley, you wanted to stop the boat that way. How long before you want to dock would you turn off the engine?
Depends on the velocity.
Yeah, it would depend on your velocity. Is it going to be a short time or a long time for a decent velocity?
You're really
A really, really long time, or really, really long time. Sir, you've known Captain Brindley your whole life. Would you say that she's a patient captain?
She said no.
No, she's not patient at all. But she doesn't have to be, because she can stop that boat in just 23 seconds. How? Just ram it into the dock. 23 seconds later and 3 city blocks, she's got that stopped. Okay? Now, that's the big idea. If you take nothing away from today's lecture, that's it. That if we want to stop that boat, change its momentum, we can either do it with a small force, the water pushing on the boat, if we're patient, if we wait a long time. Or we can do it quickly, a short time, if we use a huge force. But it's that combination of force times time that changes momentum. What changes energy? Derek, force times distance. But momentum, it's force times time that changes it, okay? We call that the impulse. The impulse. And it's just what changes momentum. It's the force times the time. But this formula, force times time, only works if that force is constant in time. It's 50 Newton. It's 50 Newtons. It's 50 Newtons. It's 50 Newtons. But that's not the way a lot of forces happen. If we hit a ball with a bat, we know that the force on that ball ramps up to some peak value and then drops down to 0 as it leaves the bat. And in that case, what we have to do is take the average force over that time interval and multiply it by the time interval. Okay? Check on your neighbor. Do a buddy check real quick. Are you ready, Willem? Okay. It is time. That's my family. A little bit of inbreeding. Okay. Now, Willem has agreed to be the assistant of death. I'm gonna have to, maybe leave my phone over here. And, let's see. This is the hardest part, at my age, is getting up on this table. Aha. I'm gonna turn 70 this year, and this was easier when I was younger. Okay. Yeah, we're almost ready. Okay. At this point, I am required by law and by the university attorneys to issue the following statement. Do not, I repeat, do not try this at home. I am a trained professional. I have not always used 1,000 nails. I started with only one nail and then worked my way up to. Yeah, really, if we park my 100 pounds on one nail, that's gonna make a big hole, okay? And I appreciate you not laughing about my saying 100 pounds. So just to make the math easier, let's say I weigh 200 pounds and I've got 1,000 nails. Each one of those nails is just gonna be pushing with 1/5 of a pound. And it's gonna take 2 or 3 pounds to put a hole in my skin. And so having a lot of nails is good, okay? But that's not what's gonna save my life. I mean, I could lay down on the floor down here and ask Willem to hit me with that sledgehammer. He'd do it, but again, that'd be biology, okay? And that'd be a mess. So there's something else that's going to save my life, and I want you to be thinking about that as I do this demo with Willem, okay? So I'm gonna put this, put that someplace safe. Thank you. Okay, and we need the chest plate first. You were gonna do it without the chest plate. That's a different demo. Okay, thank you. I'm gonna do it this way. Okay. Whoa. Safety first. There's some safety goggles over there. Okay, now, Willem's never done this before. I don't want to be breathing when he hits me. I do want to be breathing after. So I'm gonna hold my breath and say ready. And then he's gonna swing with all his mighty might. Ready. Give a hand to the official. You got some explaining to do.
I was like.
Okay. This demo has not always gone well. The very first time I did this demo 33 years ago at Montana State University, I was nervous, and I went to an older professor, Larry Kirkpatrick, and I asked, Larry, how hard should they swing the sledgehammer? He said, hard as they want. Trust the physics. You'll be fine. So I went down to my class and I asked a student who I knew from church. His name was Ralph. And I asked him if he would swing the sledgehammer. He asked, how hard should I swing it? I said, hard as you want. I'll be fine. I forgot to notice that Ralph was a giant of a man. And he took that sledgehammer and did a great big roundhouse. He came down and he missed the center of the block. He hit the side where it was solid. My arms went up, my legs went up. Half the class was afraid I was dead. The other half was afraid I wasn't. What do you do when your professor's just half dead, you know? Hit him with the cinder block, hit him with the cinder block. The other time when it didn't go well, our state was doing road shows. That's something that they used to do, and thankfully your generation doesn't have to do it. But anyway, each ward does a little play, and in between the plays, they wanted me to do different demos. And one of the demos I was going to do was the bed of death. Well, as we were going to the road show, as we were leaving the house, my oldest son, Josh, said, can I lie on the bed of death? And I said, sure. And his mother said, no, absolutely not. Not my baby. No way, no how. So Josh and I get in the car. We're heading to the stake center, and we suddenly realize Mom's not going to be there. If we keep this between us, we can get away with it. So Josh lays on the bed of death. I do a wonderful hit, not as good as Willem, but really, really good. Perfect hit. Josh was so excited to be alive, he pushed himself up off of the nails, and suddenly he had holes in his hands, and that did not play well when we got home. That was, I'm not as afraid of the sledgehammer. So I've got a question for you all. Oh, before I ask that question, I just want to show you a video. This is Larry. He was a grad student of mine. He was the same age as me. He was coming back after years out of school. And Larry had lost an arm when he was 16 in an accident. And he was very athletic. He did rock climbing, all sorts of things like that. But he really, really wanted to swing the sledgehammer. Now, in this case, he's doing it with a group of high school teachers, but we did it also for a great big, huge auditorium of students in a class. And what we did is we had a different professor ready to swing the sledgehammer. And then Larry came in at the back of the room and said, wait, you promised me I could swing the sledgehammer. And all the students looked back and said, oh, this is going to be interesting. But he had been practicing and practicing and practicing, and this is how it went. So, clicker question. Which way do we want to stop that sledgehammer? Quickly with a big force or slowly with a little force? Now you can click. I did this demo once for a bunch of Cub Scouts, a big room of Cub Scouts and their mothers. And when I turned around with this shirt, the mothers were not amused and the kids were. Okay, last call. Get it done. Okay, quickly with a large force. Okay, maybe I should have asked this question differently. Which way do I want to stop that sledgehammer? Okay, because I understand Newton's third law. I taught it to you, remember? And if I put a big force on that sledgehammer to stop it quickly, it puts a big force on me to kill me. I want to stop that sledgehammer as slowly as possible. What piece of equipment just saved my life? The cinder block. It shouldn't be called the cinder block of death, but the cinder block of life. Without that cinder block, would stop the sledgehammer almost instantly. It took time to crash through that cinder block. It was acting like a funny looking airbag. Imagine you hit something in your Toyota and suddenly cinder blocks come out of the dashboard. That's a different sort of airbag, okay? So I want to do it with as small a force as possible to stretch out the time, Now, some years ago, a high school physics teacher wanted to do this demo for his high school class. And he asked the teacher in the next room, happened to be a history teacher, to swing the sledgehammer. But they didn't have a sledgehammer, so instead they used a maul. And this is how it went. If you don't mind, I'm not going to watch.
Have to have it in the same holes that it was second. Okay. Everybody ready? Count. Like 1, 2, 3, let me know. Okay. 3.
Children.
Class dismissed.
Sure.
Oh.
Okay. Okay. The grand high equation of chapter 8 is just this. We've seen it before. That the impulse, that's the force times the time. The impulse, force times the time, is what changes momentum. Now, there's different situations in everyday life in which this equation plays a role. In many situations, the change in momentum is something that's fixed. There's nothing we can do about it. If you're going 30 miles an hour in your car and you hit a brick wall, your change in momentum is going to be some certain number that you can't change. But you can, with an airbag, increase the time during which that change happens and decrease the force. So with your neighbor, come up with at least 2 real life examples from everyday life where your change of momentum is fixed, can't do anything about it. So you try to increase the time to reduce the force. Talk to your neighbor. Do a buddy.
Guys, like.
I think the
I don't like. I don't know, an example. Stop it.
Good. Now.
It stays, maybe, you said, I don't get what it does.
That was amazing.
They're like,
You did it perfect. It was perfect.
they get softer.
Yeah.
Okay, raise your hand if you've got an example to share. In the back, all the way in the back, so that I have to run up the stairs, because why wouldn't you want to do that?
Put out our hands to kind of a little bit of force.
Instead of just doing it with your chin. Yeah, so did everyone hear that? That it's just part of our human nature that if we trip, we put out our hands with our elbows ready to give. And the same thing's true if you jump off of that table. You don't want to lock your knees to land. You want to bend your knees and flex.
Our shoes have a little bit of cushioning in them.
Yeah, if you've got good shoes, you've got that little cushion. Yeah.
Driving on the highway. If I'm driving on the highway and stop.
Okay. If you're driving on the highway and you want to stop, you want to not just do it quickly, you want to gradually do it. I'll give you an extreme example. Many, many years ago, when we lived in Seattle, the Relief Society president called my wife and said, "We're putting on a new roof. Could we borrow your husband?" And she said, "Sure, you know, take him." And she was forgetting that the Relief Society president's house was a two-story house, and I'm afraid of heights. So I got there on the Saturday morning, and I'm just terrified. All of those manly men were just walking around on that roof like it was nothing, and I'm crawling around on my hands and knees, scared to death. Well, they had a teenage son named Christian who felt the same way about this whole thing as I did, and he was crawling around on his hands and knees. But he happened to crawl onto a piece of sheet metal that just took him right off the roof and down onto the deck below. Now, it turns out that that deck was an old wooden deck, and he crashed right through it. He had broken bones. He went to the hospital, but he lived. And I went back for his, when he left on his mission, to hear his talk. Okay, he grew up. But if that deck had been concrete, he would have not gone on a mission. Okay, that deck gave time, increased the time through which he had to stop. Okay, now another way to use this equation is sometimes the force is limited. There's only so much force we can apply. And so we increase the time that we apply that force to get as much change in momentum as possible. I'll give you a quick example. The barrel of a rifle is long so that you can keep pushing on the bullet for a longer time to speed it up to a greater speed. Come up with two more examples of this sort of use of the Grant-High equation. Talk to your neighbor.
I don't know, I feel like if always do the same thing.
It's the acceleration that kills you.
Like, and at the same time, I feel like.
It does, it does get a little stronger, so you wind it more. That's why like at the end, it's like.
Okay, let's share some examples here. Raise your hand if you've got an example. Willem?
Football players, like when catching a ball, they move their hands back with the ball.
Okay,
Make it so it doesn't just bounce off.
okay, so it doesn't bounce off?
Bear Bachmeier's touchdown against the U.
Say that again, please.
Bear Bachmeier's down against the University of Utah.
Ah, well, that was something, huh? Yeah, we just kept on pushing on his back as long as we could to get him across that line. And that was amazing. Okay, that was a good example. Any of you tennis players? I've heard that you want to keep the racket in contact with the ball as long as possible to increase the speed. Is that true, or is it just to get more control? I don't know. Okay. This is a Gentile example, but when you're in a bar fight, you want to keep in contact with their chin as long as possible to increase the momentum. Don't quote me. Okay. So I've got a little wrinkle to this thing we're studying that's called momentum. My friend Jeff Adams and I are walking down the street, and suddenly we are recognized by one of our old students up on the second story. That student drops two identical flower pots down to hit our heads. The flower pots are going about 20 meters per second, 40 miles an hour when they hit our heads. For some reason, the flower pot bounces off of Jeff's head, but stops on Greg's head. If we assume that the time for impact is the same, which one of those individuals gets the worst headache? In other words, for which one of those individuals is the force on the head the largest? Is it going to be Jeff, Greg, or both the same? With your clicker, please.
I think I like it.
Okay, last call. We think we've got everyone. Okay, we're not sure. We're not sure. And that's as it should be, because I have misled you, which is just a polite way of saying I lied to you. I lied to you. I told you that momentum was mass times speed, and it is not. Momentum is mass times velocity. It is a vector quantity. Energy is not a vector quantity. There's no such thing as eastward energy or westward energy. There's just energy. But momentum definitely depends on direction, okay? And so if we look at a baseball bat hitting a ball, that ball comes in with an initial momentum to the left, and it leaves with a momentum to the right. If it leaves at the same speed that it came in at, we would say that zero change if it depended on speed, but it doesn't. It depends on velocity. And so what I would do to find the change is what I do with all vectors. I put them tail to tail, heel to heel. And then I ask, what do I have to add to this vector to the left to turn it into a vector to the right? Well, I have to add this vector that brings it all the way back down to zero and out the other way. There's the plus sign right there. I started with this, I added the change, it brought it all the way back to the right. Now that change in momentum is the same size as the impulse, which is just another word for the force times the time, Now, if we look at those two flower pots, in the case of Jeff, it had momentum down and then it had momentum up. The change of momentum is twice the magnitude of the initial momentum. But for Greg, it just went from momentum down to nothing. And so there's half the change, and hence, if the time's the same, half the force on Greg's head as on Jeff's head. Another way of thinking of that is that Greg's head just has to stop that flower pot, but Jeff's head has to not only stop it, but throw it back up into the air. See if your neighbor's okay with that. Now in Montana, it's winter 10 months of the year. And in the dead of winter, it's just icy. The streets are just slick as can be. And my friend Jeff Adams and I, at the end of the day, were walking out to our cars in the parking lot, and we had to cross this big intersection. And as we were halfway across that road, a great big old beater car that was trying to stop at the intersection hit the brakes and just kept on going. And so Jeff and I turned around and put our hands on the hood of the car, and it pushed us all the way through that intersection. I was terrified, but Jeff just looked over at me and said, "Is this one of your students or one of mine?" And so I'm just telling you who Jeff was. Okay. This is a homework problem that we're gonna work. You have a ball that's coming into that brick wall at 15 meters per second, and then it bounces off at 10 meters per second. And in this problem, you're told that it's in contact with the wall for 2/100ths of a second. And you're asked to find the average force acting on that ball. Well, we can use the impulse momentum equation, but to do that, we have to see how big the change in momentum is. My initial momentum, with the ball being 0.2 kilograms, my initial momentum is going to be 0.2 times 15, or 3 kilogram meter per second. Now you remember when we were talking about energy, we took a Newton meter and gave it a new name. We called it a joule. What do we call a kilogram meter per second? Anyone know what that unit is called? It's never been named. No one's ever named that. And so we're going to call it the Francis. Okay? And this would be 3 Franci. That's the plural of Francis. Okay? At a reunion, we have lots of Franci. I've got so many students that I think this is going to catch on, and this is the only chance I have to become famous. Okay? Now, it leaves that wall with 2 Franci, 0.2 times 10 meters per second. And the change is going to be what I have to add to the initial to get the final. That's going to be 5 Franci to the right. And that change in momentum is equal to the average force, that's what we're looking for, times the time interval that we were given in the problem as 2/100ths of a second. And so if we solve that for the average force, we get a force of 250 newtons. Do another check on your neighbor and see if they could solve problems like this on the homework.
Did it have you?
Okay,
What is that?
questions? Yes, sir.
I think you wrote it down, but I was just saying.
What's that?
You wrote it down, but like. They account for that direction of the law.
Oh, you can. You can, if you set up a coordinate system and call to the, let's say it's called to the right positive. Remember, a change is always a final minus initial. So in this case, my final would be a +2 Franci, and then I would subtract off the initial, so minus a -3 Franci. The minus the negative makes it a plus. Thank you for asking that question. Okay. Let's talk about collisions. Suppose this truck hits a Volvo, or we could say the Volvo hits the truck. And if during that collision, I ask you to find the total impulse on the system comprised of both the Volvo and the truck, okay? Well, that's just going to be the impulse on the truck plus the impulse on the Volvo, where impulse is the force times the time, okay? Now, in order to get those forces, I'm going to draw free body diagrams. For the truck, I have a big force down, weight, and a big force up by the road. And then I have this force by the Volvo on the truck, a normal force. For the Volvo, I've got a smaller weight, a smaller force up by the road, but I have a huge normal force because it's a great big truck.
Makes sense.
I'm waiting. No, because the truck was speeding. No, because the truck was speeding and heavy. No, those two forces are equal and opposite by what law? By third law, okay? And that means that when I add up the impulse on the truck and on the Volvo, for the truck, I've got that normal force by the Volvo on the truck times the time. For the Volvo, I have the normal by the truck on the Volvo times the time. Well, I think we can agree that if this collision lasted 1/10 of a second for the truck, it also lasted 1/10 of a second for the Volvo. And so those time intervals are the same. Now, this impulse is to the left, and this impulse is to the right, and they're the same size. So when I add them together, I get 0. I get 0. That means the total impulse on this system is nothing. And remember, it's impulse that changes momentum. So if there is no impulse, there is no change in momentum. Okay? We say momentum is conserved, and that is one of the most powerful principles in all of physics. Momentum is conserved. Okay? Now, my promise to you is that if you include everything in your system that bumps, hits, collides, by Newton's third law, the impulse on that system will always be zero. And that means that this is the Grant-High equation written another way. The impulse in the morning is always equal to the impulse at night. I did not say that, and if you say I did, I'll call you liars, okay? The momentum in the morning is equal to the momentum at night, unless there's an impulse that's changing the momentum. Well, if you include everything in, oh, I've got cinder block in my shirt. Oh, that's uncomfortable. Okay, if you include everything in your system that collides, that impulse is going to be zero. And then the equation becomes this. Momentum is conserved. And I mean the momentum of the system, the momentum of the truck plus the momentum of the car. Now let's think about what that means. When I said energy was conserved, I had to do a lot of hand waving. If we ignore air resistance, or if we ignore the heat that happens when friction takes place, all sorts of different conditions in order for energy to be conserved. And that's because there were all sorts of these different buckets of energy that we didn't have a handle on, okay? But there's only one bucket for momentum. And so when we say momentum's conserved in a collision, we mean every collision. It can be a messy collision involving C4 explosives. It doesn't have to have any kind of hand waving at all. And that makes it a powerful, powerful principle. But there's a caveat. And that is that when we were talking about energy, we could choose our initial and final to be anything we wanted it to be. But when we're looking at a collision, initial means right before the collision, and final means right after the collision. You can't wait for that car to slide across the pavement and end up in someone's yard, okay? It's right before and right after, okay? Now, here's an example. Suppose we have two identical Volvos of 1,200 kilograms. I use Volvos because I can draw them. They're simple to draw and no one gets hurt in a Volvo. They're both going 30 meters per second, 60 miles an hour. And my question to you is, what is the total kinetic energy of that system comprised of the two Volvos? And these are your choices, 0, 36,000 joules, or 1,080,000 joules. So talk to your neighbor and then use your clicker to vote.
Going in the direction that might be zero.
But I don't think kinetic is the vector, so I don't think they're gonna.
What's the law?
Energy is.
Yeah, oh, yeah.
Because it's asking for the kinetic energy.
Yeah, okay.
Oh, but it's.
30 times
Where?
Where they're at.
30. Oh. There's still that much. Ready? What?
Okay, go ahead and get your vote in. Okay, last call. Okay, 1,000,000 and change there. Now I have a question for these people that voted 0. What were you thinking? And I'll tell you what you were thinking. You were thinking that car has a bunch of right going energy, and this car has a bunch of left going energy, and the right going energy cancels out the left going energy, and you got zero. But there's no such thing as left going energy or right going energy. It's just energy. And so when I calculate that energy, I just take the energy of the left car and add it to the energy of the right car. And you notice that when I plug in the speed, I've got this minus sign here because it's going to the left. But I just wasted, I guess, shadow is what I wasted, because I'm going to square that. And so it's going to go away. And so what I get is 540,000 joules for the left car, 540,000 joules for the right car, or 1,000,000 joules and change. Now I want to point out that this much energy, and that's a lot of energy. Two of those Volvos going 60 miles an hour have a large capacity to do damage. That's a lot of energy. But in your home, that's the amount of energy that would light a 100-watt bulb for 3 hours. And in Utah, that would cost you 4 cents. That's a lot of energy for 4 pennies, okay? Now, I'm not trying to say that you should waste electric energy. I'm just saying you shouldn't ruin your marriage over it, okay? You shouldn't be hassling your family about turning off the lights. There are bigger fish to fry, okay? The exception to this is if you've got an electric dryer, just put a bullet through that, because that's just, you know, if you go out and look at your meter, that's just causing it to spin like crazy. This is not going to be on the exam, but when we first moved to Bozeman, we were invited to a party given by one of the, a doctor in the ward. And this doctor was just, he was quite a character. And all night long, he was just ragging on his wife. He was just, you know, giving her grief. And then he told a story about how he came home from a hunting trip. And when he got home, she had every light in the mansion on. And then to beat the band, she came out onto the porch and turned on that light as well. And by then I had had enough. I had just had enough. And I said, JD, look, if she leaves all the lights on all month long, you're going to pay an extra $60 in a month. I took my daughter to your clinic and I had to pay $300 just to look at a wart. If you want to save money, don't go to you. I was never invited back. I do not understand why, but anyway, don't let this ruin your marriage. Okay, what if I were instead to ask what's the total momentum of the system? Well, now that's a vector, and the direction matters. And the right going momentum is going to cancel the left going momentum. Because now when I use a coordinate system and I put in this minus sign, it doesn't get squared. It's still a minus sign, and I get 0. Now remember, any collision, if I include both cars, is going to conserve that number. If it's 0 before the collision, it's got to be 0 after the collision. So what has to happen after that collision? What do they have to be doing after the collision? Well, one option is they could stop. That's 0 momentum. But I could also have them bounce off going 30 meters per second the other way. That's 0 momentum. And anything in between. I just chose a number 10 meters per second, but I could have chosen any number there. As long as it's the same for both, that adds up to 0. So I need to know some more information before I can tell you what happened after that collision, okay? Now, let's look at the mechanical energy, which in this case would be kinetic energy. I started out with 1,000,000 and change in joules, and in this collision, I lost it all. But in the bottom collision, I didn't lose a single joule. None of it got lost. In the middle one, I lost most of it, okay? Now, here's a question. Suppose you were on the corner when this collision happened, this collision at the bottom, and the police come and they talk to you and they say, What was it like? What did you see? What did you hear? First of all, what did you hear? Was it loud? No, it's silent. Sound is energy, and you didn't lose any energy, so there couldn't be any sound. How could you make that collision on the bottom happen? What would you have to do to make that collision be a reality? Talk to your neighbor real quick. What would you have to do?
Man,
Yeah.
Yeah, I don't get.
Okay, what ideas do you have?
Shoot diamonds at each other in space.
Okay, and it's got to be diamonds because why not?
There's no, if it's not, then they might break and that's energy.
Okay, so you got to do the whole thing out in space so that you don't have any sound going on. Okay. Okay, what if we wanted to do it on the street corner, by the street corner where you saw this? That's going to be harder. Any ideas?
Road was icy, would that help?
If the road was icy, you'd hit the brakes and just slam into each other, but you'd bounce. But then I'd hear that.
You had bumper cars?
Okay, bumper cars, did it come in and thunk? You're almost there, but I still heard that thunk. Springs, doing. I still heard the doing. Okay. The only thing I can think of is if you've got a great big north pole of a magnet and a great big north pole of a magnet so that they come together and don't ever actually touch. It roll. Okay. What I'm trying to get across is that's hard.
Magnets.
That kind of collision happens once every blue moon. Almost never, almost never. Okay. We call that, well, first of all, where does the energy go? Well, in that first collision, it goes into messy buckets like heat and sound. And most of the energy goes into what we call the energy of deformation, to take the frame of that Volvo and just mess it up. And we don't have a formula for that kind of energy. Not just we in this room, but we as humans. That's just too complex. Every car is different, okay? And that's why we don't use energy to solve a collision problem. Every collision problem is a momentum problem. And when you get to that next exam, every question is either going to be an energy problem or a momentum problem. And if you try to solve an energy problem with momentum, you got no chance. If you try to solve a momentum problem with energy, you got no chance. So the first thing you ask yourself is this a collision? And if it's a collision, momentum. You use momentum, okay? Now, we call this kind of collision that only happens in a blue moon elastic. We call this collision where we lost some energy inelastic. And in the special case where the bumpers lock and it becomes one ugly Volvo with 8 wheels, we call that maximally inelastic. Maximally because it loses the most energy allowed by law. What law? Newton's third law. Newton's third law. Okay? Now, I have here 3 surfaces. I've got a rubber surface, I've got a steel surface, and I've got a glass surface. This they gave me when I left Bozeman. I finally have a use for it. And what I'm going to do is I'm going to bounce a rubber ball on the rubber pad, a steel ball on the steel, and a glass marble on the glass plate. And you're going to have to answer which of these collisions is most elastic. But first of all, let's ask ourselves, what would an elastic collision look like? If I drop this ball from this height and it's a perfectly elastic collision, how high would it rise afterwards? All the way, all the way. So with your clicker one last time. Which collision is most elastic? Okay. Last call? Okay, rubber on rubber. Okay, let's check that out. Okay. Rubber on rubber. Okay, that didn't go very high. Steel on steel. Even less. Glass on glass. Whoa, okay. Glass on glass was the answer. Now, here's why I did that. We've already found that in some cases, words that we use in everyday life, like work, don't mean the same in a physics class. Okay, and elastic is one of those words. In everyday life, something that's elastic deforms like an elastic rubber band or a rubber ball. But in physics, elastic means you don't lose any of the energy. And when something deforms, some of the energy goes into the deformation, causing the deformation. So the glass ball was the one that had the most elastic collision because it didn't deform, because it was rigid, because it didn't change its shape. And hence it had the most elastic collision. Okay, now this is where the morning class ran out of time. So why don't we stop here and have a great weekend, folks. Thank you.